Okay, so we've been talking about obviously gases here. And last time we talked about a couple of things as well. We talked about excuse me, the combined gas law, which really does have all of the sort of variables that you could come across in a sort of gas law problem. As we also talked about, is sort of a useful one because, again, you could pretty much get all those other sort of gas laws we saw at the beginning of this chapter from this one. You basically just eliminate whatever is being held constant or whatever information you really don't have. And again, like you cross out the temperatures there, you'll have Boyle's law and so forth as you go through it. We also talked about calculating the density and molar mass of gases. Density, again, typically on grams per liter, and molar mass is obviously grams per mole. As we talked about last time, there's a couple of those equations that you can just remember if you like, but really, as we saw in those couple of examples, it's really all based off of sort of the ideal gas law. So with the information sort of given to you, you could kind of use the ideal gas law, and again, more like a dimensional analysis unit sort of conversion, and you'll be able to really sort of figure out both the density and the molar mass of a substance. So I think where we are at then after that is let's continue on. All right, so where we laid up was talking about gas stoichiometry, or we got really to sort of gas stoichiometry. And gas stoichiometry works really the same way as all the stoichiometries, basic stoichiometry, solution stoichiometry. The main difference is, again, here you will have really those same four steps, and you'll want to balance the equation. You want to convert to moles. You'll want to do the mole to mole relationship from the equation, which is really the stoichiometry part. And then you want to take those moles to some other unit. So really, it's the same sort of four steps as a traditional basic stoichiometry problem, although you can definitely have a limiting reagent sort of problem in gas stoichiometry. I would say probably most of the time it'll just be really more of a basic one, but you definitely can still have that limiting reagent sort of situation that could occur. The only difference really is somewhere along the way, you use a gas law, and it's usually is the PV equals nRT. So it's really kind of two places where you could use this. I would say probably most common is a lot of times you're interested in how much gas you would produce, or the volume of gas that you would produce. So a lot of times we will use it there in the end step, and in a lot of cases we will be kind of solving for the volume, is a lot of times how we'll use that. And really the moles part here would come from the stoichiometry, so that kind of mole-to-mole relationship. So very commonly you'll have kind of a traditional sort of stoichiometry problem at the beginning. You may even have grams or something like that you convert to moles, and then you go through, and then really at the end you kind of stick the moles into the ideal gas law and solve for volume. The other potential place you could use it is actually at the beginning. And if you were to use it at the beginning, you would most likely be using it to get the moles. So that's sort of the other sort of option. So if you were going to use it at the beginning, you would get the moles here, PV over RT. So those are really sort of the slight variations that we have with gas stoichiometry, but pretty much everything else is the same. And as I mentioned before, probably most of the time you might not come across too much of a limiting reagent sort of situation in these type of problems, but you definitely still could. And the same rules still apply if it happens to be a limiting reagent situation. The way, again, you can still recognize that is you're able to get to the moles of each of the reactants. So if you are able to do that, you should obviously take that into account. But again, probably in most cases, it's going to be more of a basic stoichiometry sort of problem, where somewhere along the way there, you'll use the ideal gas law. So if we look at a problem here, why don't you give it a try? What is the volume of CO2 that's produced at 37 degrees and 1 atmosphere when we take 5.6 grams of glucose, which is this guy right there, is used up in this reaction? And we'll give you some numbers that will be helpful. Carbon 12.01, hydrogen 1.008, oxygen 16. Okay, let's take a look. So it's obviously a stoichiometry problem. It involves a gas that we're looking to find the volume of. We do have temperatures 37 degrees Celsius, and we do have a pressure of 1 atmosphere. So that's really all of our sort of gas information, which usually means PV equals nRT is going to be used. In this case, we have pressure. We're looking for the volume. We do have the temperature. We always have R. So really, in order to sort of solve for it, we will be missing the moles here of the CO2. And we need to get to the moles of CO2, and we could do that from the 5.6 grams basically of our glucose. So this is going to be sort of a basic stoichiometry problem. We're going to balance the equation, which it already is. We're going to take this information here and convert it into moles, which is what we want to really do here. So in this case, we have, we got there 6 times 12.01. Plus 12 times 1.008 and 6 times 16. Looks like gonna give us 180.2, I think, grams per mole, give or take. All right, so now we have the molar mass. We will do that conversion. So we're going to take our 5.6 grams of C6H12O6. And by the way, this is just a basic stoichiometry problem, as obviously I could get the moles of that guy, but I have no information about that guy, so I don't have to worry about limiting reagent or anything like that. So we'll do that conversion here, 180.2 grams per mole. That's going to give us 0.03108, we'll call it, moles of C6H12O6. In this case, we're going to do then the stoichiometry part. So we're looking for the mole-to-mole relationship between those two. And we can see that it is a 1-to-6 relationship there from the equation. So that would be our next spot here. We want to get rid of the glucose. So we'll put that on the bottom. We want to end up here with our CO2 moles. And our moles here will cancel. So we're going to basically multiply that by 6, it looks like. Gives us a 0.186 moles of CO2. So this particular problem is pretty straightforward, like a regular stoichiometry problem up to this point. And this is really where the difference is going to come in. Instead of maybe figuring out how many grams of CO2, we want the volume. So we're going to use the ideal gas law here to do that. And in this case, we are going to solve for volume, which is nRT over P. Now, in terms of our values here, we're in atmospheres for the pressure, so that's good. We, much like normal, need to add our 273 here to convert our temperature into Kelvin. And then I think we should be good at that point. So putting in our numbers, we get our moles that we calculated through stoichiometry. We have our gas constant, which we always have. We got our temperature converted into Kelvin, and our pressure was already in atmospheres, which is good. Again, atmospheres will cancel, Kelvin will cancel, moles will cancel. That's going to leave us liters at this point. We will end up with about 4.73 liters of CO2 would be produced in this case. This would be our theoretical yield in this case, based off of this per action. Any questions on that one? So again, still really the same 4 basic steps, which is sort of that insertion of the ideal gas law there at one of them. Any questions on any parts of that there? All right, let's try another one then, make sure. Magnesium reacts with hydrochloric acid to produce a gas, which you'll do next week, I think. So we want to know, calculate the volume of hydrogen gas that's produced at STP by 5 grams of magnesium and HCl. So magnesium is like 2431, I think. Okay, so again, here we have a stoichiometry problem. We want to start with our balance equation, which it looks like it is. We have how much volume of hydrogen gas at STP. So remember, when we do have STP, it does mean 273 Kelvin, and the pressure is 1 atmosphere. So once again, for our gas that we're looking for, we do have pressure, temperature, we're looking for a volume. So again, using our ideal gas law, just kind of not checking off things. We got temperature, we got pressure, looking for our volume. We always have R. So once again, in this situation, we're going to use really the ideal gas law at the end to get some moles. But in order to do that, the only other piece of information we have is 5 grams of magnesium, which is where we're going to start with the basic stoichiometry steps here. So we're going to take our 5 grams of magnesium, using the molar mass of magnesium, 2431 grams per mole. We're going to get 5 divided by 2431, 0.2057 moles of magnesium. Once again, here we're not interested in magnesium. We are interested in hydrogen, though. So we're going to use stoichiometry to go from magnesium to hydrogen. And in this case, it is a 1-to-1 relationship, which makes it pretty easy. 1 magnesium, 1 mole of hydrogen, going to give us 0.2057 moles of hydrogen. So again, very similar to a basic stoichiometry problem. At this point, we now have the missing piece that we need there for our ideal gas law. Again, solving for volume, which would be nRT over P. Our moles of 0.2057, our R 0.08206, and our temperature of 273, and our pressure here of 1 atmosphere. Once again, atmospheres cancel, Kelvin cancel, moles cancel, leaves us with liters. And if we do this here, 0.2057 times 0.08206 times the 273, we end up with 4.61 liters here of H2, would also again be our theoretical yield in this particular case. Same 4 steps: balance equation, convert to moles, mole to mole relationship, and again, converting those moles to some other unit. Questions on that particular one? Now, as we talked about earlier as well, because this is at STP conditions, if you did not want to use the ideal gas law, you could use that at STP. 1 mole is equal to 22.414 liters. So at this point, you could have picked off that number and use that conversion without using the ideal gas law again, because it was at STP. And it will get you there as well. So again, it could have shortcutted it because it was at STP. Any questions on that there? Yeah. Why would it be Ziga? Here, because coefficient is a 1 here, so that's where the stoichiometry comes from, the coefficient. Yeah, so 1 there and 1 there, so that's where the all comes from. Other questions? Okay. Now, also, as we talked about earlier on in this chapter, again, in terms of stoichiometry, if you happen to be at again, constant pressure and temperature conditions, remember that you can kind of do a volume to volume relationship like we did earlier, without maybe having to go through kind of the mole sort of aspect of it, and you can get right to the volume. But again, that is if it is pressure and temperature where they are constant, and that would be again like Avogadro's sort of relationship that we talked about earlier as well. Any questions on stoichiometry? All right, then let's talk a little bit about Dalton's law of partial pressures, which seems really hard, but the idea here is fairly straightforward. If we have a container, and inside that container, the only gas molecules we have are the same gas molecules, like A, flying around, then the total pressure of that container is really all a result basically of the pressure that's being contributed by the A gas molecules that are flying around. Now, if we have a container where maybe we got A molecules, maybe some B, I'll try my alphabet here, C as well. And we got all these guys basically flying around in the same container. They each are basically contributing to the overall pressure. So in this case, the total pressure would be the pressures from gas molecule A plus the pressure from gas molecule B plus the pressure from gas molecule C in this particular case. And these are what are referred to as partial pressures, because they are partially contributing to the overall pressure of that mixture. Now, this is one of these sort of areas where, as we talked about as well, I think the other day, the ideal gas situation kind of comes into play. One of the things that makes something an ideal gas is that there's really no attractive forces or repulsion type forces between different gas molecules, even though they're in the same container. So although in the case on the right there, we have 3 different gas molecules that are present, we could basically assume that they're in the container by themselves, as the other gas molecules flying around will have really no effect on their pressure. And what that basically means is in most of these sort of partial pressure situations, it is just the ideal gas law. So it is just the ideal gas law that you solve for P. And you would do it for basically all the different gases that would be in a mixture. Now, one of the nice things about it being in a mixture is all these gas molecules are basically in the same container, which means they pretty much all have the same volume. And because that container is sitting in the same room, they all have the same temperature. And since R is a constant, pretty much the only thing that will vary between your sort of ideal gas law calculation for the different gases is how many moles you have of each of those. So everything else will be the same because, again, they're sitting in the same container. So you basically would use the ideal gas law, obviously making sure everybody's in the proper units to use the ideal gas law. You get all the pressures. Those would again be called the partial pressures. And then you simply just add them together and that'll give you the total pressure of what is there. Questions on that there? As we see here. Now, there is another sort of way that we can calculate partial pressures in addition to the ideal gas law, although that is a very common way. And in this particular case, if we do not have enough information, maybe to go into the ideal gas law, so maybe they don't give us a temperature or anything like that, we can use what is referred to as the partial pressures and our X, which if you remember from the previous chapter, that is our mole fraction. So if we have enough information to figure out our mole fraction of all the gases that are present, and we know pretty much just one thing, we either know a partial pressure of one of the gases or we know the total pressure of everybody, we can basically figure out all the partial pressures of the other gases by using this equation down here. So that is the partial pressure of a gas, that is the mole fraction of that gas, and that is the total pressure. So this is a very useful sort of equation when you run into a situation where you maybe don't have enough information to go into the ideal gas law, but you do have at least the moles of everybody, or can figure out the moles of everybody. And again, just that one other piece of information, be it the total pressure or at least a partial pressure, and you'll be able to basically figure out everything else. So that's a useful sort of formula there. Remember, again, the mole fraction is pretty much the moles you're interested in divided by the total moles. It is not a percentage. So again, we don't multiply by 100 there at that point. We just take the point something type of deal. Any questions on that there? All right, so let's try some here, see. All right, I got 5 grams of helium and 5 grams of neon in a 2.5 liter container at 27 degrees. What is the partial pressures of both gases and what is the total pressure in ATM is fine. Neon is 2018. And helium is 4.003. Okay, let's take a look, see how we're doing. So we obviously have a mixture of gases here. So partial pressure situation, we've got helium, we've got neon floating around in the same container. Again, the consequence of ideal gas law is doesn't really matter that they're in there together. We could almost think of them as being in there by themselves. So we do have 5 grams of helium. We also have 5 grams of neon. And in this case, we do have a volume of 2.5 liters. We also have a temperature 27 degrees Celsius. Since it's a gas, we know we need to convert it anyways here. So that's going to give us a 300 Kelvin. We are looking for the pressures in each of these cases. So we really are missing the N, but we could get that from the grams. And we're pretty much good to go here. So we will convert our grams into moles. So we got 4.003 grams per mole. We also will do that for our neon, which is 2018 grams per mole. And remember, in these type of problems, that's pretty much the only thing that's different. Again, the temperature and the volume should be the same for both, as they're in the same container. And that will give us something like that feels wrong. Try this again. Divided by 4.003. That didn't look like 700. All right, so 1.24 moles. We'll call this guy, and we'll go 5 divided by 2018. 0.248 moles. So now we really do have moles here. So that's check. So we do have everything we need. We're just going to do basically 2 separate ideal gas law calculations. So we'll do it for helium first, and that means it will equal nRT divided by V. Everything's in the right units now. So taking our moles for our helium, taking our gas constant and our temperature, all divided by our volume of 2.5 liters. Going to give us 1.24 times 0.08206 times 300 divided by 2.5, about 12.2 atmospheres. That would be what is known as the partial pressure of helium in this case. We're going to do an identical calculation for neon. Again, the only difference going to be our moles. So we want to obviously use the moles of our neon, which is 0.248. Everything else going to be identical here, again, because they're in the same container. And at this point, we end up with 2.44 atmospheres. And that is the partial pressure of neon in this case. Any questions on either of those calculations? At this point, the total pressure will be the contribution basically of both of these gases, the helium plus the neon. So in this case, we'll take 12.2 plus 2.44 atmospheres, and that will get us about 14.6 atmospheres as our total pressure in this particular case. Any question on any of that there? The one that's contributing the most pressure in this case is which one? It is the helium. Any ideas why that would be? We will talk about it in just a second, but it is actually the molar mass. Yeah, helium is a much lighter gas, which means it's going to be able to fly around a lot faster, which means it's going to cause a lot more collisions than the heavier, slower moving neon in this case, as you can see in the difference in the pressures. Any questions on that there? All right, let's try another one here. A sample natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure is 1.37, what is the partial pressure of propane? Okay, let's take a look at this. So this also is a mixture of gases. In this particular case, we have the moles of everybody, but we do have the total pressure, but we don't have anything else in terms of temperature or volumes and stuff like that. So here's a situation where the ideal gas law might not be helpful in this case. So that other sort of partial pressure one that we saw that looks something like this, where we take the partial pressure equals the mole fraction times the total pressure. We could use this because we do have the total pressure. We do have everybody in terms of moles, so we can figure out the total moles here by adding everybody together. So that's going to be 8.24 plus 0.421 plus 0.116 moles here. And that's going to give us a total moles of, I believe, 8.77, I think. So in this case, we are interested in propane, which is this guy here. So we'll do the mole fraction of our propane. And that would be the moles of the propane divided by the total moles. And again, here, no multiplying by 100. So we'll take 0.116 divided by 8.777. Going to give us a mole fraction of 0.0132, basically 1%. And we're then going to put that into our formula here. And we'll take 0.0132. We'll times it by the total pressure, 1.37 atmospheres. And that gives us a partial pressure for this guy of about 0.0181 atmospheres. You could obviously do the same thing for the other two gases there, get the mole fractions of each of those and multiply them by the total pressure. It's really sort of the percentage that's available there of the total pressure. Any questions on that one? Obviously, a variation of this is you have things in grams, got to go grams to moles and then get the moles fraction and stuff like that. All right. So those are two different sort of ways that we come across sort of partial pressures, which are very common. And the third sort of partial pressure situation is really extremely common, especially when you're doing experiments involving gases. A lot of times when you collect a gas, usually you oftentimes will collect it in water or over water. And usually it's a situation where you collect the gas comes in, water goes out, basically. So the gas comes in and basically replaces the water. In a situation like this, you got some potassium chlorate, you heat it up, going to generate a bunch of oxygen gas, going to go through the tube all the way through. This was obviously filled with water. So as the oxygen comes in, out goes the water, and it basically displaces the water that was in there. Now, a consequence of sort of doing this and collecting the gas with water is just the process of the reaction that's occurring. In addition to oxygen, in this particular example, you also get some water vapor that comes along for the ride because it's being done in water, a little bit of heat, you get some water vapor and something will come out for it. So this is really a partial pressure situation. And in most cases, you're not interested in the water's contribution. You're interested in really just the gas you're trying to collect. So in this example, it would be oxygen. So in this case, the total pressure would equal the pressure of the gas you're interested in plus the vapor pressure of water is what that is sometimes referred to, the vapor pressure of water. The good news on that is that usually is in most cases in the textbook type problem and even in a laboratory, a value you look up in a table. So you look that up in a table based on the temperature. So a lot of times we will do a sort of correction calculation when you do experiments like this, whenever water is involved in the collection process of a gas. To get the pressure of the gas by itself, you basically take the total pressure and you subtract it by the vapor pressure of water. So it's sort of a correction calculation. And sometimes people will refer to that as getting the pressure of the dry gas because you're basically subtracting off the water's contribution in this case. So sometimes that's what it's referred to. So it's always a case like that. And sometimes keywords that you see in sort of textbook problems is the gas was collected over water, or it mentions something like it's saturated with water vapor in the question. So those are like the keywords that you know that you do have to sort of do this sort of correction sort of calculation. Questions on that? So that's a very common sort of partial pressure situation that occurs whenever we do collect that gas with basically water. Here's a table, as you can see, of vapor pressure of water. So again, the good news is it's really just a table value that you could look, and it's really more like a correction sort of calculation. So let's take a look at an example of this. If we were to do an experiment just like we just saw in that picture, and we collected oxygen gas saturated with water vapor. So again, that's sort of the key words that you sometimes will commonly see in sort of textbook problems that tell you got to kind of do that. At 30 degrees Celsius, the total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. Here's where the temperature comes into play, really in this type of problem, only to look up on the table to get the correct vapor pressure of water is basically what it would be. In most problems, this would be a value you would have to go look up. And a lot of times they don't give it to you in the actual problem. And there should be a table, obviously, in your chapter that looks like that. So basically, we have that situation that our total pressure is equal to the pressure, in this case, of the oxygen gas plus the vapor pressure of water. The total pressure is given to us as 753 torr. By the way, in the laboratory, the total pressure would be your barometer reading that you would take for today. That would be your total pressure. So the pressure of oxygen gas, it really just kind of boils down to a subtraction sort of situation. And that would mean we would take 753 torr, which is our total pressure. We would take our, only 2 R's maybe. We would take our table value there for the vapor pressure of water at 30 degrees. And we would subtract them. And in this case, we will end up with 753 minus 31.824. Going to give us about 721 torr. It does want it in atmospheres, so we will have to do our torr to atmosphere conversion. That's our 760 is an atmosphere. Divided by 760 gives us a 0.949 atmospheres as the pressure of the oxygen gas in this case. Again, sometimes referred to as pressure of the dry oxygen gas in this case. Any questions on that calculation? So those are sort of 3 different sort of partial pressure situations that does come up a lot. Basically, it's just a straight into ideal gas law. If you don't have enough to use the ideal gas law, but have enough to get the moles and some type of pressure value, that partial pressure one with the mole fraction. And then this is, again, a very common sort of partial pressure situation. Any questions on any of those situations? Okay. So you touched upon a lot of this here as we've gone through the different sort of gas laws, but this is the kinetic molecular theory of gases. And again, the couple parts in here that, we sort of talked about that make something an ideal gas. Let's just sort of highlight those as well. A gas obviously is composed of molecules that are separated by distance. They can be considered points, and they basically possess kind of no volume or negligible volume. And that, again, is one of the things that make something an ideal gas. That's why we, again, really focus in on the volume of the container the gas is in rather than the volume of the gas itself under ideal conditions. And that's really, again, one of those things that is what sort of an ideal gas is. Gas molecules are in constant motion and directions, and collisions among them are perfectly elastic, which means, they just bounce off each other, no real effect on kind of their speed or anything like that. And again, has no effect on the pressure. The third thing here is the other thing that really makes something, again, an ideal gas is gas molecules neither exert any type of attracted or repulsion type forces. So this guy here as well is what makes something an ideal gas. And those are the 2 real big things. The volume of the gas is basically negligible, and there's really no interaction between different gas molecules. They have no effect. Why would interactions or effects be important? And it's because if you just think about a gas molecule heading towards, say, the wall, if there was another gas molecule it was attracted to, it would kind of slow down its path, right? So when it hit the wall as hard or as quickly. Also, if it was, say, unattractive or repulsed by the other gas molecule, it would move away a lot faster and it would have an effect on the overall pressure. But in an ideal situation, we don't have that effect sort of happening. And again, that's really why what we just did there with partial pressures, we could consider, even though they're all in there together, that the kind of each gas is in there by itself. They're really not going to have any type of interaction with one another. The average kinetic energy of molecules is proportional to temperature. So as we've talked about, you kind of raise the temperature, you expect gas molecules to move faster. If you lower the temperature, you expect them to kind of slow down as well. Now, again, some of the relationships that we saw with those equations, we saw our Boyle's law, again, as the pressure goes down, the volume goes up and vice versa. We saw our Charles law relationships, again, pressure is proportional to temperature. That's what the little symbol there is, a proportional symbol. And again, as pressure goes up, so there's the temperature in a situation where we have a constant volume and it doesn't adjust, as we talked about. And again, volume will go up as temperature goes up in a situation where the volume can adjust. And again, that is what keeps us at our constant pressure that we talked about. And again, some of the other relationships that we talked about, again, Avogadro's law, the pressure is proportional to the moles of gas that are present. So obviously, if you have a lot more moles of gas, you're going to have a lot more collisions and probably a lot more pressure as well. And vice versa, if you have less moles of gas, you'll have less collisions and less pressure that will happen. Again, no attractor repulsion type force is really important for our partial pressure situations. And again, basically just all the gases together make up the total contribution there of the pressure. All right, so this is an apparatus that you can use to sort of study molecular speed of it. And there's sort of detectors that spin around, and obviously slower molecules end up on sort of one side and sort of much faster molecules end up on the other side of the detector here. And we can actually calculate the speed of a gas. And if we look at a couple of different comparisons, the first chart up here on the left is the speed of nitrogen gas at 3 different temperatures. And what we see is at 100 Kelvin, it's kind of maxing out the speed about there. As we drop to 300 Kelvin or go up to 300 Kelvin, we're going there. And obviously, as we increase the temperature there, we're going there. So as we see for a particular gas molecule, as we increase the temperature, we do see the average speed or velocity of that gas increase. And the opposite would be true, obviously, if you lower the temperature, we'll see it sort of slow down in terms of that. Now, if we look at the difference between different gas molecules and temperature, we see that chlorine is moving much slower than nitrogen, which is moving much slower there than helium. And the difference here is what we were talking about a second ago. It is the molar mass difference. So chlorine is about 70 grams per mole. Nitrogen is 28, and the lightest of all those there being our helium at 4. So it's moving much faster. And this is all at the same temperature. So in comparison, at the same temperature, because helium is a much lighter gas than, say, chlorine, it is moving much faster. You could actually calculate what is referred to as the root mean square velocity. And that's what that stands for. It is the square root of R times T, which is our temperature in Kelvin, and M is our molar mass. So this is our Kelvin. That's our molar mass. And this molar mass actually needs to be in kilograms per mole rather than grams per mole. And the reason for that is actually our R value here. The R value is not the R that we've been using for the ideal gas law. It is the 8.314 joules per Kelvin per mole version of this. And the reason it is a joule is equal to a kilogram meter squared second squared. So it is actually this version of the gas constant that's used for this equation. And that is because if we do this here and just look at the units, if we use those units for R, which would be kilograms, meter squared, second squared, Kelvin and mole, basically. And we use our temperature, which is Kelvin, and we use our molar mass that has to be in kilograms per mole. The kilograms cancel, the Kelvin cancel, the moles cancel. That leaves us the square root of meter squared over second squared. And when we take the square root of that, we end up with units of meters per second, which is the velocity units. So the R value is really the same number, but what it means is we do have to use our molar mass in kilograms for everything to properly cancel out as meters per second. Any questions on that there? So let's take a look at when we do the two gases, we did the partial pressures first. Let's do our helium and neon at 27 degrees Celsius, I think was the temperature. So what is the root mean square velocity of that guy, of each of those gases in meters per second? And helium again is 4.003. And neon is 2018. All right, so calculate it up, see what you come up with here. Okay, let's take a look. So we're going to calculate the root mean square velocity. We'll do it for helium first. So we're going to take the square root of 3 times 8.314. Again, that's kilograms, meter squared, second squared, and Kelvin and mole. Where our temperature, we do need to convert to Kelvin. We did it earlier in that problem. So a 273 will give us 300 Kelvin. And also here, our molar mass needs to be converted to kilograms per mole rather than grams per mole. So it's just a kilogram conversion, which means divided by 1,000, or move the decimal place 3 places to the left there. Gets us 0.004003 kilograms per mole. And if we do all that good stuff there, 3 times 8.314 times 300 divided by 0.004003, and then not forget to take the square root would be good. All right, we take square root of it. We end up with about 1,367 meters per second is the root mean square velocity, or how fast basically our helium is moving at 27 degrees Celsius. A question on that calculation there. So let's take a look at what our neon was moving at here. Basically going to be the same calculation, except obviously we'll use the appropriate molar mass there. So our 8.314 for Kelvin per mole, our 300 Kelvin. And again, here we'll divide by 1,000 or move the decimal place a couple of places over, 3 places over really. And that will give us kilograms per mole. Again, here everything's going to cancel. That joule is our kilogram, meter squared, second squared. So if we do that, we got a 3 times 8.314 times a 300 divided by 0.02018, taking the square root of it. Going to give us about 608 or 9 meters per second here as our root mean square velocity for neon. The one that's moving much faster is helium, right? Much lighter, moving about twice as fast. For reference sake, you know, that's about, I don't know, maybe 1,369, I think, miles per hour is neon. Helium is moving about 3,000 miles per hour. Yeah, so it's moving much, much faster than that. Any questions on that calculation there? So again, that does relate to like the problem we saw earlier where, again, helium was coming in about 12.4 atmospheres, right? Versus the 2.4 atmospheres that neon was contributing in that particular problem. Any question on root mean square velocity here? Another sort of aspect of gases is gas diffusion, and that's the gradual mixing of gases with one gas and another gas by virtue of their kinetic properties. So I think we got a bottle here of NH3 and a bottle of hydrogen chloride or hydrochloric acid. When they come together, they make ammonium chloride, which is this white sort of smoke that you can maybe see there. And if we look at it here, we notice that basically the NH3 comes out, right? The HCl comes out. The mixing is occurring closer to which one? Is happening closer to the HCl. Again, based on what we just talked about, which one should be moving faster? The NH3 should be moving faster. It's lighter, right? So it moves faster. It's able to get way over here. The slower moving HCl coming out of the bottle doesn't get as far. So we see the mixing actually occur closer to the slower moving bottle there as the fumes come out. We can actually calculate that, and using this equation here, R1 over R2, that's the rates at which those gases are moving. And M2 and M1, these are the molar masses. And here you can use grams per mole. It's all good because we're not using, obviously, the gas constant here. So if you know the rate at which one gas is moving and the molar mass of that gas, and maybe the molar mass of the other gas, you can figure out the rate at which that gas would be moving as well. Sort of similar sort of formula that's used helps us with what is known as gas effusion, which is a little bit different. And this is the process by which one gas under pressure basically escapes from one compartment to the next through an opening. So like these guys popping through that hole to the other side. We could actually use pretty much the same equation there. Rate 1 over rate 2 equals our square root of our different molar masses. This is also time, basically the time it takes it for one gas to get somewhere versus the other. So you could also use time rather than rate as well. So in this case, if we look at a problem like this, nickel forms a gas compound with a formula of NiCO(X). What is the value of X under the same conditions? Methane goes 3.3 times faster than that compound. So if we get the molar mass here of methane, which is 12.01 plus 4 times 1.008. So we have CH4 has a molar mass here of 16.04. We could call this M2 if you want. M1, we're not sure what it is. This is grams per mole. We do know that R2 is moving 3.3 times as fast as R1, right? It's 3.3 times faster than R1, basically, in this case. So if we put this into our formula here, we'll do R1 over 3.3 of R1 is equal to the square root of M2, which in my case I did 16.04 grams per mole, and my molar mass of my unknown compound in this case. In this case, although we don't know the actual rates, we do know that these two will cancel, and that will give us basically 1 divided by 3.3 gives us 0.30303 is equal to the square root of 16.04 over our missing one. To get rid of the square root, I need to square both sides, right? So I'm going to square both sides to do that. And if I square both sides, that gives me 0.91827 equals 16.04 over our M1. M1 is going to go to the left, and we're going to divide. So M1 will equal 16.04 divided by 0.091827. See how I did there with the math here. Going to give us a molar mass for our unknown compound, about 174 we'll call it 67 or 68 grams per mole. First off, any questions on that calculation? Now, I know I called CH4 the second one. You could call it the first one and just keep those together. It really doesn't matter which one's which, as long as, again, the values go together. So how does this help us? Well, the one thing that we know for our unknown is nickel. So if we go to periodic table and look up nickel, and we can see it maybe it's like 5868, I think. So I think nickel is 5868, if I could see that. 68 grams per mole. So I know for sure that I have one nickel in my formula, right? So if I take 174.68 and I subtract nickel's molar mass, which I know for sure is there, provided I read that number sort of right, that'll give us 174.68 minus 58.28, gives us about 116.4 grams per mole. That 116 is made up of basically a carbon and oxygen unit, right? And the carbon oxygen unit is 1201 plus 16, which basically means each of those carbon oxygen units have a molar mass of about 28.01 grams per mole. So if I take my 116.4 divided by 2801, gives me approximately, we'll call it 4.1-ish, about 4 of them basically. So the missing sort of guy is approximately a 4 in that case with that. So this is one application that you could use it for to figure out sort of a missing formula. You obviously could just straight up figure out the molar mass of a compound or the rate or time it takes one other compound to move across. Any questions on gas effusion or diffusion? All right, we'll lay it up there for today.